Can start. We did. Oh, is this frozen again? I could have sworn I unfroze it. We did this example of Newton's laws. I'm going to bring this down in just a second so you guys can see, but I want to be able to look at it and then I'll bring it down. Where we had two masses attached by a rope hanging from a pulley, and we did some math work here. We took a video of this, right? I'm going to post the video of this and post these notes up online so that you can see them. But big picture, what I just want to show you right now, we used these two definitions, right? The velocity is dx dt and acceleration is dv dt. And we took advantage of the fact that I can manipulate this derivative stuff as a fraction to break it down and set up an identity here that will give me, I guess I should probably delete that and that. That will give me something that looks like this. A dx equals v dv. And fun fact, it didn't click at the very beginning when I first started looking at this, but this equation, this setup here, is actually going to give us our third kinematic equation. That vf squared equals v initial squared plus 2a delta x. That's what this gives us. It's not just from algebra.
Delta x is dx.
Delta x is dx. Yeah, and when I integrate, that's where I'm going to get this thing from. So just fun facts. Today we're going to keep going with some Newton's law stuff. Except, not this one. I'm going to re-edit them, but I have edited them around a little bit, taking feedback from people just to make it a little bit easier to read. So we're going to look at a very special case of forces. This isn't really using special forces per se, but there is a special system, a special arrangement or physical way that I could describe my forces. That was really loud. Where using our regular coordinate system makes things a little bit difficult for us. So the ramp is really special. Because if I take a look at our ramp, I've superimposed here our xy coordinate system. This thing is going to move which way? Down and to the left. It will move two-dimensionally. The acceleration of this system will actually point. It's okay, I don't need to draw. It's all right. Can I draw? Nope, can't draw. The acceleration will actually point that way. And notice that acceleration is, did it stop? Okay, well, that acceleration is two-dimensional. And that kind of sucks. Let's kind of show how badly that really sucks. You don't have to copy all of this down. I'm going to do a sample problem with this. I'm going to put it up online so you can do it. Just kind of follow along and see if you'll get what I get. So let's say I had this exact scenario right here. I have a block of mass 100 kilograms, and it's on a perfectly smooth, frictionless ramp. All right? Everybody's with me on that so far? Yeah. And what I would like to know is, with what acceleration will this system move? What will this feel? So what should I start with? A fibida. And my free body diagram is actually going to be really simple. I can't draw on the picture because I don't know why I can't draw on the picture. I don't know why I can't draw on literally anything. This let me draw before.
Wait, it says force of weight is 900.
As soon as you pick up the pen.
Hello? Sure. As soon as I pick up the pen.
Like you had to click the drawing, and then it would click, and when you pick up the pen, it unclicks.
So let's click that.
No. What's that number, by the way? It's
980 newtons because weight is mg and the mass was 100.
Okay. Yeah.
So now I got to figure out, you know what? How about we do this? Since this is being really difficult, let's add a new thing there. Let's make this transparent. I said transparent. There we go. And let's draw on that. Will that work?
Force? When you say force, is that magnitude?
Which force?
Force of
Maybe
the weight?
if you
Force,
click on
weight?
the pen.
Well, the direction is the vector pointing downward.
Have you tried clicking on the pen?
Okay, there we go. finally. So let's draw a free body diagram. I'll have my force of gravity pointing downwards. Which way will my normal force go? Perpendicular to my surface, which will go like that. Okay? Now, looking at this free body diagram, we can tell really quickly and very easily that my system is not at rest, for sure, because there's no x component to balance this thing out. Even if I didn't know what this thing was, just looking at this free body diagram tells me that this is for sure not going to go down. All right, I know that this is 980 newtons. I also know that this angle here is 30 degrees. So what that tells me is that this angle here is 30 degrees. Is everybody okay with that?
Wait, I remember like doing this, but I don't remember why it's...
Well, if this, let's go through. We can do, how about we do some similar triangle stuff? We can go through a series of similar triangles. Here I've got one, and here I've got another, and then I'm going to do another one over there. So if this is 30 right here, what does that make this guy here? Also 30. So this angle right here is also 30. So then how do I go from here to up there? Does anybody know?
Where to?
Let's do, hold on, let me see if I can make this bigger. So the goal is to figure out what that angle is, right? That's the goal. So I've got these two parallel lines here and here. I want it in a different color. So that means here is a bisector here. So if this is 30, then this right here is 30, right? Wait, not that one. It's not that one. It's... No, that'll be consequence, but... Okay, it's the fact that this is not there.
Because this would be 60.
Yes?
Go over, that's 60. Meaning the one in front of it is 30.
Yes?
Meaning the one above it is 60.
Come here and draw it. I want you to draw it. Mostly because I hate geometry, but I want you to draw it.
No, like I'm not gonna lie, that could be.
If this is
totally
30,
off.
then this is 30.
But I can't write small stuff.
I don't care.
Okay.
Doesn't matter.
30, meaning
Yes.
this guy's 60.
Yes, that's what I had.
Meaning this one's 30.
Oh yeah, and then these two are vertical angles.
Yes.
Okay,
Yeah.
that's an easier way to go. Yeah. Okay, so let's take advantage of, I wanted to use alternating interior, but you can use vertical.
So then 60, and then above it is 60.
And then you can
And then in
use,
front of it's
yeah.
30.
Okay, so he took advantage of vertical angles. It would be easier if you thought of, and it makes no difference really, this line right here going through the center. It makes no difference. It's the same thing. Does that make sense? If this is 30, that means that this right here is 60, right? Does that make sense? That means that the angle from here to here is 60. So these two angles here are the same, right?
Yeah.
And this right here is 90, so this angle has to be 30. And if these two angles are the same, then this has to be 30 as well. Well, I was going to go with alternating interior angles. That's what I was going to go with. But vertical angles works just as well. Okay. So are we okay with this statement, that that angle there is 30? All right. That means I can break this up as force normal x and force normal y. And then I can start writing out some of my free body diagram stuff.
What do you mean an FGX and an FGY?
That's what I was going to say.
Because
Where would there be an x component here?
but
No,
it's
force,
your
normal
X.
force is.
Because in
force of
this
gravity.
case, your normal force is the one that's
Two-dimensional.
gravity.
Yes.
right. So gravity isn't just pulling it down. It's
No,
pulling
gravity's
to the
pulling it
side.
down.
Gravity is, right now, gravity all it's doing is
No,
pulling
the
it down.
force of gravity is doing that,
That's
but
it.
then normal force happens to be the x component.
Yes.
Right.
So in my regular,
Yeah.
no reason to believe there's anything else that I should do, my gravity force goes straight down, and my normal force has two dimensions. And I can write I'm actually going to write them a little bit higher up so that I have room. My sum of forces in the y will be that normal force y minus force of gravity. We have already established that this system is going to move down and to the left, so this should have a negative ma, and a sum of forces in the x, which would be normal force x, negative, and this is moving to the left, so it should be negative max. This would be negative may. Does that make sense? Is that okay? Is that fine for everybody so far? Now this is kind of unfortunate because normal force has no equation. I mean, I could expand this a little bit. I could rewrite this as n cosine of 30. And I could rewrite this as n sine of 30.
Wait, why?
Where do you see your g?
Why is it equal to negative m?
Well, because I know that this thing is moving down. It's accelerating downwards.
Oh, okay.
So it should be negative because it's going down. But it's also accelerating to the left.
In order to find, though, your normal force, you need to have your FG. You need to find the hypotenuse of your FG.
Well, there is no hypotenuse for FG because FG is just that.
FG times the angle.
You guys are already doing what the trick is, and I'm not doing the trick. I'm giving you justification for why we do the trick. There's a reason why. There's a reason why. This is why. You guys saw it, she did not. So we're just going slowly. So this starts to suck. It really does.
I just don't get where you get negative n.
This part?
Sine of-
Because that's this x component here, and that would be up here, and that's the opposite side of my angle, so it should be sine.
Oh.
And just like cosine is adjacent, so I would get n cosine. Now, I know this. I know the mass. So I could kind of find certain things. I can kind of get somewhere.
Yeah, exactly.
N would be my normal force. My normal force that points two-dimensionally.
We're solving normal force.
Actually, what I want to know is the acceleration. That's the goal. I want to figure out what my acceleration of the system is. And looking at this, who can give me some possible methods of solution? How can I solve this equation? Because I don't know ax, I don't know ay, I don't know n.
You can do, what's it called? Pythagorean,
I could do what?
Pythagorean.
Pythagorean theorem? How so? What would you like to do for Pythagorean theorem?
Well, because you don't have your N anyway, so I won't get you nowhere.
So what would you like to do? Well, big picture, we could try to do some substitution stuff. Let me rewrite these equations really quickly to make them look a little bit nicer. So equation 1 would be n cosine, I'll keep it as theta, minus 980 newtons equals 98 kilograms times ay. And equation 2 would be negative n.
Wait, is it 100?
Oh yeah, you're right, sorry. You're right. Negative 180 theta equals 100 kilograms times ax. So this is what I've got. This is what I know. How do I solve? What do I do to solve? What can I...
Your N.
I can solve for n? Well, in the bottom one, I've got two unknowns. I technically could have one more equation. I know something about ax and ay. I know that ax squared plus ay squared is a squared. I know that. Right, this is truth. So big picture, what could I do? I've got three equations and what? And three unknowns. I could solve. This is totally solvable. I could...
You know your theta.
I do know theta, right? So I right now, what I could do is I could replace this. Sine of 30 is what? 1/2? It's 1/2. And cosine of 30 is...
That doesn't really get you any closer.
No, it doesn't. It just makes things pretty. It just makes things pretty. But big picture, think about what could I do? 3 equations, 3 unknowns. What could I do? What's the only thing I could do? Substitution. I would have to do some type of substitution. And for the record, how pretty is my substitution going to look? You know why? You want to know the one thing that's making my substitution look really bad? This third one. Yeah. Taking this squared and then square rooting things is going to make my substitution look really ugly. It really will. But it is solvable, right? I know this because algebra guarantees me a solution as long as I have an equal number of equations to unknowns. I could do that. It's going to take me quite some time. Thankfully, some of us were already there. Thankfully, where did it go? What? Okay. Okay. I mean, that's cool. You don't have to listen to me. Thankfully, there is a solution to the ramp that we can take advantage of and make our lives really easy. We could take advantage of the flexibility that coordinate systems offer us to make them much more user-friendly for us.
You can
Okay?
do the Fn is the y.
I can rotate. Yes, I can rotate my coordinate system, and suddenly, if I do this, certain things become very, very pretty. So I've got a simulation that we can kind of play with, just to see.
Like the ramp is the x.
The ramp, yes. Okay, I had a simulation. Oh, okay, it's finally doing something. Hopefully it will continue to do something. And this is going to be our pretty much our one and only case where we're going to have to do this. The nice thing is that coordinate systems have a lot of flexibility in them because they don't exist. They're not real. Like they're not set in stone. You can manipulate them however you like, as long as you're very consistent. The only real rules of the XY coordinate system is that x and y are orthogonal. That's it. That's the only real rule for them. Perpendicular to each other. As long as x and y are perpendicular to each other, it doesn't matter which way they are pointing. It doesn't matter where this coordinate system is. As long as they're orthogonal, I can always define any point in space as a combination of x's and y's. Really? I already had this. I already had this. And then you're going to take literally 80 years. I did this beforehand. Why are you doing this again? Okay. Okay. But I need to turn this up. Because I would like to do that. And I don't want that. Well, whatever. Oh, no. Good enough for me. Just like the situation we had a second ago, if I have a coordinate system or a setup where my ramp is very slippery and I have no friction, my free body diagram will look like this. And then my normal regular coordinate system, my normal force is 2-dimensional, but so is the resultant acceleration. Because the resultant acceleration, we notice, is parallel to the surface of the ramp, and it goes down and to the left or down and to the right, whatever. If I take my coordinate system and I rotate this coordinate system, oh no, okay, that didn't do what I wanted it to do. Oh, it won't let me do it. Okay, whatever. Go back up and pause right there. If I take this coordinate system, this x, y, and I make a brand new coordinate system, and I'll call it nothing. I'm not crazy that this worked before, right? Like it did work before. I'm not insane. Okay. If I take this coordinate system and I rotate the whole thing, I'll get I can now get a new coordinate system. We'll call this y prime, and y prime really goes with force normal. That's what it does. It goes in the direction of force normal. It's parallel. And x prime is, everybody knows what this notation means? Say it again.
Parallel.
It is parallel with the surface of the ramp, which means that my resultant acceleration in this case is no longer two-dimensional. It will be one-dimensional with respect to x prime. And when I do this, certain things change a little bit. If I go back to my problem, yeah, they've been doing this all day. Yeah? If I take this system and I rotate its coordinate system, I hate everything.
I've never seen anyone fighting with a whiteboard.
Yeah, I wish I could just... Thanks, man.
No, Hebrew teachers end up writing with Excel markers on
Oh, wow. This was working totally fine last week. Like, everything was totally good last week. And then now, for some reason, it wants to not draw when it should be drawing, and it wants to not do the things that it should be doing, and it wants to just be a big, giant pain in my rear end. Okay. It probably is. Don't... If I now have my new y primes and x primes, for the record, what's the angle? We already proved it last time. It's theta. It's the angle of the ramp. It's theta. By the same token, vertical angles, what's this angle? The same angle theta. Okay? That's really important. Because when I draw my free body diagram with reference to this coordinate system, my normal force becomes one-dimensional, but my gravity force changes and becomes two-dimensional. So before I had a free body diagram that looked like this, and we had an acceleration vector that points that way, which was annoying. When I rotate, I'll have a normal force that points up like that. When I rotate around, my gravity force will end up pointing this way with my angle here, and my acceleration is going to point which way? One-dimensionally to the right. And this is where you can see exactly which force is actually producing the acceleration. Because it's not really the normal force that's making this thing move. It's not moving because the surface is pushing this thing. It's moving because some part of gravity is causing this thing to move. And it's not all of it, because we could measure this and find that the acceleration that this thing goes down with is going to be less than 9.81. It's got to be some value less. And if I look at it, here's my x component. It will be some value of mg sine theta, because it is opposite of that. And before, when we looked at the old problem, we had this really crazy 3-equation thing that would have gotten us the exact same answer as if I take a look at this and said, the sum of forces in the x is what? Mg sine theta, negative, right? Because it's going to the left. And this should equal negative ma. So what is the acceleration? Negative mg sine theta. That is the acceleration. We would have gotten the exact same answer if we would have done it the other case with our 2 dimensions. It would have taken us a significant I'm trying to use a much nicer word than what I had in mind, but a not so nice pain in the butt method of solution. It would take a significant modicum of effort to get to the same value. If this thing were to be pointing the other direction, totally fine. Our free body diagram will just be reflected over the y. Totally cool. That's not a big deal. Now, by convention, usually we take the down the ramp direction to be positive, just because which way is this thing going to move? Yeah, gravity's always going to make this thing move down. 99 times out of 100, it's so much easier for us to make down the ramp positive than it is to make it negative. In this case, usually, it makes life much easier to do it that way. But that's okay. Questions? This rotating thing is really helpful for the ramp. Not so helpful in many other cases, but super helpful for the ramp. Usually, you'll probably start with this one. That's usually where you're going to go. I would recommend practicing until you get familiar with it, and it'll make your life much easier. Did everybody? Wow. He was really upset, though. Han is dead. Like, come on. Like, he's sad. All right, he's sad. Did everybody see the homework posted up online? Right? Everybody did it? Yeah. I'm going to post up another set. The solutions for your book are also going to be up online. So you can double check. Yeah, I did. They finally sent it to me. I'm not 100% sure if they want me just posting them. I don't care. So whatever. Just don't publish them anywhere. I'm trusting you. Except to you. I'm not going to let you have them. That look was like, you're like,
I made a deal with a guy.
Oh, dude, that's the sketchiest thing that I've ever heard. I'm going to put up some more questions for Newton's laws just for practice. There are a couple small details for Newton's laws that I want to go over, and then we're going to kind of touch back on kinematics, because we're going to see circular motion of kinematics. Because now that we've got forces, we can now understand what's going on when you move in a circle. Because if you're moving in a circle, what must you have? No. Well, big picture, an acceleration. Because in order to move in a circle, your velocity vector needs to change. It has to change. And without understanding why, without understanding that there must be a force that's causing this acceleration to be there, then we're just going to say there's an acceleration. Magically. For some reason. And that's not very useful. But now that we have an idea kind of forces, who remembers where forces come from?
Contact or from gravity?
Fields. Contacts or fields. So when I look at something that is moving around in a circle, then the question is, something has to either be touching this object to make this thing move in a circle, or there has to be some kind of special field that is making this move in a circle. For the record, the most common field that makes things move in a circle is gravity, and this is why the Earth rotates around the sun. That's the reason why it does that. Just why the moon rotates around the Earth. That gravity force is acting like a centripetal force. We'll get there in a little bit. The centripetal force, remember when we were first talking about forces, we said there were 5 special forces. There's a reason why the centripetal force is not on that list. It's not a real force. It does not actually exist. Same deal. That's even less real. But centripetal is a force that is not real, but it is a force that acts on an object and pulls an object in towards a center. A centrifugal force is something that pushes something away from the center. But, fun fact, and I'll test you on this later, guess what it is that actually pushes you away from the center?
Normal.
Inertia. Inertia is what pushes you away from the center, because what is your body, as you're moving around and around in a circle, what your body wants to do is move in a straight line. That's what it wants to do, right? Your body wants to do whatever it was doing. Right? Inertia is the tendency of an object. It will keep going straight. Inertia is the tendency to resist changes. It's actually the tendency to resist acceleration, really, if you think about it. Have a great day, guys. You guys